somewhere around 2012, I hope. Maybe 2012. Yes, 2012. I don't know whether Hemanand is there in this call. Hemanand, Prativ Raj, we are all were working in ZF, the company, and there we did this particular project of retrofitting our air handling units with electronically commutated brushless DC fans. Okay, and we attained some significant savings. Okay, but that is not the purpose. This particular sharing I did maybe in 2014 in the Urjavaran at Pune and Mumbai. Okay, but in Vishakhapatnam, I want to give a different perspective for the people. Okay, so what a continual improvement can give people the advantage. Okay, all these ISO requirements, be it 9,000 or be it 50,000, sub emphasis on one particular aspect, that is the PDCA cycle. And this particular plan, do, check, act cycle has to continuously go on. So it is the continual improvement of, which will give the advantage for any organization. Okay, so what we did maybe in 2012 or 13 is retrofitting the conventional induction fan induction motor driven centrifugal fans into an EC BLDC fan. Okay, and we got some significant savings. Okay, this is the analysis of why this saving we are getting with respect to the Shanky of where how and all there are losses in a conventional AHU fan driven by an induction motor, and how with an EC BLDC fan the losses are significantly getting reduced, both the mechanical losses, electrical losses, as well as on the maintenance aspect. It is even now, though I am not with that particular company now, but I am hearing like there is a ease of maintenance they are having, and I don't think they had any breakdown. I don't know, any of my ex-colleagues from ZF is also there in the call. If there is something you face as a problem, you can also share that. Okay. And this is why it is giving saving. Okay, I'm skipping all these things. Very important is the part load energy efficiency of this particular fan. That's also very important. Why this is very important is data analytics without domain knowledge is nothing. Okay, so we need to understand how data analytics can give the savings for the people. So we need to compare the performance of our machines with respect to the variables which can be there. One of the very important variable is what is the load we are having. Okay, so what is the load we are having? Sometimes in winter we have part load condition. In summer we may have to I don't know 110% or 120% load also will be there. Okay, but this particular fan is capable of even we can increase the speed to a certain level without having any problem with the mechanicals. Okay, so that is another advantage what we had. And there is another advantage. I think this is the research work. I think this is Hemanand. Yeah, Hemanand did this research along with PSG PG students that time. It was from the power electronic department. I don't remember the name, but it was someone named Rekha. They were there in the plant and they did this analysis. And those days, that Fluke power analyzer was used for getting the data. And they came with a very different finding, like after retrofitting a conventional fan, induction motor driven by a variable speed drive, this EC BLDC fan is also giving very less harmonics. And very important is the harmonics is there in a certain order only. So it is very easy for us to mitigate it with a passive filter. So that is another thing what we did. And this I remember there was one more student from Akshaya College of Engineering. He also has the name Balasundaram. His name is, okay. Now he is a design engineer in a very leading company. Okay, he did an analysis of how the computation fluid dynamics kind of analysis, and he tried to see how the energy efficiency of this particular fan after this retrofit can be improved. Um, may I request the organizer to mute the participant's mic, please? Okay, I'm getting some disturbances. Okay, Balasundaram did this particular analysis of how after retrofitting, there were a lot of engineering improvements, which is further possible to improve the energy efficiency of this particular fan. Okay, and he modeled it in 3D space, and he did the CFD analysis, and finally he told like, sir, I think you have to, I checked the noise level. Noise level is very less even before the noise alternator. But this particular noise alternator is consuming some energy. The delta P between the noise alternator is also there. Whereas, as per the norms or the standard, we don't need this particular noise alternator. I don't recall the values, but he did that particular study, and then we came to the management and appealed like we are going to remove the noise alternator and we are going to see. And straight away we got very good savings. But this is another analysis he did. Okay, and one other aspect, what he also suggested is one is the noise alternator, second is the space, what is getting generated within the AHU. The AHU room is so designed for the big centrifugal fan driven by an induction motor. I recall it was somewhere around 25 kilowatt or something like that. But after this matrix configuration of EC BLDC fan was fitted, there is a huge amount of space was also there, and he also gave an idea how we can create a funnel kind of mechanical modification inside the AHU with the GI sheets, and how we can avoid. Okay, so this is the next analysis he did. Okay, so if you can see, the first part is changing the the first thing is we can mute all the mics. Is it possible? Except mine. Friends, whomever is joining, kindly mute your mic, okay, immediately after joining. Okay, fine. So what happened is, iteratively, step by step, we improved. Okay, first the changing of the VFD driven induction motor to a EC-BLDC fan, and after that we found there are some good savings in terms of a harmonic mitigation also. And then we came to the CFD analysis, and we tried to reduce the losses, mechanical losses, which is also happening, and especially the noise oscillator and this converging funnel kind of thing. So this is the step-by-step improvement what we did, and every year we had some kind of saving after that. Okay, then this is the saving we got. Okay, I'm just skipping it. I skip all these things because this is not relevant for this particular topic. Okay, yeah, this is very important. Then after this, my management gave an opportunity for us to visit Infosys. It was maybe 12 or 13, 2012 or 13. Okay, we went to Infosys, and we were very impressed with what Infosys have done in their Bangalore campus. They were working on radiant cooling, they were working data analysis, they were having something called an energy command center. Okay, where they are monitoring almost some Singapore, some 10 or 15 buildings, UAE, some buildings, and they were saying like they are monitoring the data, having the baseline for each and every mission for different operating conditions, and whenever there is a deviation, they raise a ticket, and the ticket goes to the maintenance team. Okay, that is the inspiration which drew me and my team towards data analytics. Okay, so then we thought like, okay, where we are. Okay, then we had a small discussion, and we found like we are having the data from all these BLDC fans. Okay, all these BLDC fans we had. Okay, and this particular data is coming to us in terms of Modbus telegrams. I think that was my another student from Malaysian University, Petronas University, who came back in his final year for another work, and he did an industrial Internet of Things, connecting all these particular fans, and there were people from PSG Tech instrumentation department who helped me to decode the Modbus data frame. And we don't want to go with some the software which is given by IBM Paps, who is the OEM of that particular fan. We developed our own algorithm because ZF wants that. Okay, and we did it in LabVIEW, and the data is now with us. Okay. And now again, a lot of data is coming. Okay, so with this particular data, what to do? That is another important aspect what we had. Okay, then we started reading some literatures. One of the literature is the Industrial Internet Consortium's publication in 2017 on how IIoT and data analytics can go together. Okay, I also request. I have one more PPT in my ResearchGate repository talking about the Industrial Internet Consortium standard, and you can please go through it. That is very essential because we say like we can handle all the data, but we have to keep in mind what are all the practical difficulties, and how this data have to be digested, and what is edge analytics, why edge analytics important. And this is the very important chart in the IAC stating like from the sensors, whatever data you are getting, you have to extract a feature out of it, and that using that particular feature, you have to develop the model. Okay, because all this particular data, what is coming, the accelerometer data, the proximity probe data, the thermocouple data, maybe in our case, in the EC BLDC fan, it is the current data which is coming. So all this data is high-speed data. We cannot work with high-speed data, especially with the latency what we are having in the internet or the internet what we are having. And there are a lot of algorithms, supervised and unsupervised techniques are available. I think in our last classes, we had a small brief of what this algorithm all about, and what are all the advantages, why they call this as supervised or unsupervised. I think you also have, I gave the link of that particular website. Hope you all played with that and might have some decent understanding of what is machine learning topics all about. Okay. Then we started taking this particular data and doing some data analytics. In our first class also we discussed like exploratory data analysis is the first part. Okay. After that comes the creating the model. Okay. In this particular model, creating the baseline is very important. Creating the baseline is very important, and this is how a baseline is created. Under ideal condition, how this particular age you have to perform. This is the baseline what we are creating. And when this particular baseline is getting created, whenever there is a deviation from the baseline, we tag this as abnormality. We talked about outlier and other things also in our previous classes. Okay, so this is how in real term we do the data. Use the data. Okay, and now with this COVID kind of situation, Corona kind of situation, I also discussed with my colleagues in ISRE, and they want me to take one more session on how remote servicing can be done. Okay, so what is remote servicing? People cannot travel, and there are a lot of restrictions by the government to curtail the number of people traveling, remote support and other things. And after this remote support, what people will also look at is what is the value I'm getting because of the remote connect. Okay, and in remote, what you will get only data. Okay, the pictures, maybe video, you can get something. Say you are having an AMC annual maintenance contract with an AMC manufacturer, and he can do a remote diagnosis of the machine, and he can certain models and to predict what is going. What I want to give as a premier or last time IAMP we made a small demo thing. So I'm just opening this because it's very important to have an understanding. So what we did is we created some historical data, and with this particular historical data, we try to predict what is the new data, and we calculated the data, and we saw whether this particular data is on this side or this side, whether it is very near to the line or not. Okay? So here, this is the baseline. The historical data here gives me my baseline, okay, how my x and y should move. And the equation y is equal to mx plus c gives me the equation of the baseline. And when a new data comes, I'm comparing this particular data to the baseline, okay, and I'm seeing the how much is the difference, okay. And majority of the time, if it is on this side, say this is my operating hours, x is my operating hours, okay, and y is my energy consumption, I would always have a desire that this particular new data have to be below this particular line. So if it is below that line, what does it mean? I am operating the plant at a high energy. Okay? Hope you are able to get it. Let me just rename this. I will add a label. Okay, maybe here this is my operating condition. Say how much percentage I am operating my plant, and this is my kilowatt hour, or how much energy I am consuming. Okay, if this particular point is below this particular line, then I'm okay. Now there is one more small indicator I want to introduce called R square. R square. The R square value here is 1. It is perfect. The R square value of the fit between X and Y is perfect. It is a straight line because it is a synthetic data. So I am there. Now, what I'm going to do is, in this particular copy, I'm going to disturb the variable. Okay, a, this is my new. This is my old graph. Now my new graph. In my new graph, I'm just clicking on the same line. I'm adding the trend line. Okay, and I'm saying, okay, maybe how it is. And I'm saying you also display the equation and my R square. So you see here, now I have disturbed the data, and you see here what is the R square value I'm getting? It is 0.6. So I'm getting a less R square value because this particular line, which is drawn by the system based on the equation of say some ax square minus bx plus c, okay, is not perfectly fitting with this. A lot of errors. Okay, I have created this error. So the R square is a value which gives me the degree of fitness. Whatever I am predicting, okay, how close I am predicting the truth. This is R square. So this is the basic understanding which we need to have. Like this, there are parameters, okay, which will give you an indication how to fit this. And based on this only, accuracy of any model is calculated. Now, going to our problem. I think this is something which we saw last time. Okay, uh, loom, okay, textile loom, and in that textile loom, we did a small analysis of how this particular loom can work. Okay, and if my loom have to operate with less number of breaks, how I can have this particular loom managed with a set parameter. The new parameters. I mean, say I am having a different type of wool. Say because of the corona kind of situation, I'm not getting a wool bee from a supplier. supplier, I'm only getting wool A. Then if it is wool A and say I am having less number of manpower and I have to operate only in certain looms, then what is the tension I have to operate by which the number of breaks can get reduced? Because we talked about we focus on not the absolute energy consumption, we focus on how much the energy is giving value add. Okay, so we are focusing on the relative energy consumption. So how efficient a plant work is very important. What we are going to do in fixed assets like a compressor, fan, and other things will get saturated maybe after 5 or 6 years. But after that, what where you can optimize is your production. How you can reduce the rejections, how you can reduce the rework, which will consume more energy. Okay, so this is what we saw. Okay. Now, as discussed last year, last data set. So this is also something which I recommend. Maybe students and youngsters, whenever you are having time, okay, please go to some website like a Kaggle, okay, or a UCI or a PhysioNet repository where some medical major data also will be given to you. Try to take that particular data and do some analysis. Here I was doing some analysis on a sepsis. We are having a lot of ICU conditions now, right? So in ICU, there is one event called as sepsis. That is like our blood will get poisoned or something like that. I don't know. But you after sepsis, the life of that particular patient, they will count in hours or days. Okay, so the condition is very crucial. And the current data set, what was given outside is when this particular sepsis is getting detected by the doctor, okay, will a data scientist can help the doctor to predict this at least 6 hours before a clinical prediction. So a doctor predicts, say, at a time T, can a data scientist with the available data from an ICU, can he predicts maybe T minus 6? That is the challenge they have given. I'm not so passionate about participating in the challenge, but I want to learn how data science can really add value for you. So that is another thing what I request all the participants. Whenever you are having time, please attempt some open challenges. Okay, by you can. So here I am trying to import one of the file which we discussed last time, which is a file called CCP. It's combined cycle power plant. Okay, and this particular combined cycle power plant, was so this is the uh, data set they give. Okay, like this. Okay, and this data set talks about a combined cycle power plant. There is a good paper on this. Actually, one of the publication, which also I request people to go through it. Okay? How for grid or something like that, how the degradation can be reduced. Of the paper which I saw, prognostic of for health management, power industry. So download this and have a look. So we go to this particular data set. Correctly, reading the data. Let me see how this data is. Okay. So this data, as I told, this is a combined cycle power plant, and you are having a PE. PE stands for produced energy. Okay, so the energy what this produced. Okay, the maybe a generator. Okay, and what the variables we are having is the ambient temperature. V stands for some vacuum pressure. Okay, and AP is the ambient pressure, and RH is the relative humidity. And with this particular four variables, will we be able to predict how much is the energy what this power plant can generate? Okay, so this is the data set. What is given for the open world? This can also download. It is called as a CCP, combined cycle power plant. Um, why, what I'm doing is this particular data set is like a symbol, PL symbol, converting that into data frame for EV R program. Uh, in our next classes, I'm going to introduce you one of the very easy open source program, okay, which is graphically you can use your tool and do some small analysis of it. There were a lot of requests like if there are some zero code kind of a platform, will that be available for us to do some home work or training? Okay, so for that we are planning for a open source tool. So now I have done the data preparation. Okay, let me explore the data and see how it is. Okay, the first and foremost, what I'm going to explore is with respect to the ambient temperature. AT is the ambient temperature. I am trying to explore how much will be the power it is produced. The graph I'm getting. Okay, the graph I'm getting. What this graph says. Okay, same like in our Excel. We made this Excel, right? So X and Y, we have made a scatter plot and we try to fit a line. Okay, same way you can see here, I can also fit a line. Okay, but what is the difference? Maybe compared to the thing what we have seen, have something like this here. Okay, but here, what is the difference? What is the difference here? Any idea? See, what we have seen in the Excel is having a line like this. Okay, but what we are seeing here is a line like this. The direction of the line is here. The direction of the line. That is the difference what we are having. And the power output here is inversely proportional to the ambient temperature. When an ambient temperature is increasing, the power output is getting okay. When an ambient temperature is less, my power output is high. So this is the meaning what this particular data gives. So this is the indication what this particular graph is. Now I have one more variable which is the vacuum, exhaust vacuum. We have to really see what this particular vacuum hearing films. But again, when you are doing a data science kind of work, don't go much with the engineering. Only understand what it is, okay, and with that make a sense out of it. Otherwise, it will not really add value. So it should be something like I know this is a power plant, but I don't want to go into detail how this power plant has to work and other things. Okay? I will try to understand or learn from the data what I'm so here, it is not so good like our the earlier graph. Okay, like our earlier graph. Our earlier graph is almost a straight line cluster. Okay, there are only few outliers. There are few data outside. But here, in this particular graph, okay, in this particular graph of vacuum, you can see it is a little distracted. Data see here there is a scattered data. Scattered. But again, if I normalize and I say like, okay, reality, but what is the proportion? Here also, it is not directly proportional, it is actually inversely proportional. Okay? So when the exhaust vacuum is getting reduced, I am having a higher power. Okay? Okay, and at the 40, maybe I don't know, bar or something, okay, I am getting a high production of power. Okay, whereas if my vacuum is somewhere around 80, I am getting so. But again, there is a huge variance. Okay? It is not a very closely packed, clustered, or clumsy kind of data set. Here it is a little uh, different. Okay, it is loosely packed. Okay, so here also we are having an inverse proportional relationship, but not so strong, like our earlier one. So let me see what the other variable is giving us. The other variable is ambient pressure. Okay, ambient pressure versus the produced. Let me execute this particular command. Okay, don't worry, even I don't know what is this particular command all about. Okay, but what I will normally do is I will make when undergoing some training, I will copy like, okay, using a ggplot for making a scatter plot. These are all the code required, and where and all I need to modify it. So what I am doing here is I am taking the data power plant, and this particular arrow mark is I am with this particular data, I'm going to plot, and what I'm going to plot, the x-axis is the ambient pressure, y-axis is P, means the produced energy, and in what way I'm going to plot, I'm going to have a point plot. That means it is a scatter plot, okay? And what should be the color? It should be red. And what should be the size of the point? It should be 0.3. If I increase it, it will be much bigger, okay? Then what should be my title? It is atmospheric pressure. Yeah, what is the X label? This. Y label? This. Okay. And this is something theme which normally I will copy and paste it because this is something good and as a good look for our graph. Okay. So now if I give this code to you after this particular session, this becomes your master kitty bag, and have this particular kitty bag whenever you are having some problem. Use this kitty bag. During that particular session, I have seen they are using the ggplot like this. Let me copy it. I know where and all I have to change the data. Instead of power plant, you are using some other data. You change the name of that x-axis, y-axis, you change the name. You don't want point, you want line, you change this particular thing. Like that, you have to customize it. You should know how to customize it. That's all. Okay, don't try to mug up all the line of codes which may not be required in this particular era where internet is available for us to help. And many of the platform like RStudio also will give you help. So can someone give a idea of about what is the relationship between atmospheric pressure and power output? Um, uh, Whether this particular relationship is good or bad? Okay, do we have a good relationship or a bad relationship? Can I have some chat um, responses, please? The relationship between atmospheric pressure and the power. Okay, relationship is bad. Okay, relationship is very poor. Okay, relationship is very poor. Okay, good. Now, can anyone tell me whether if I say like okay, there is a relationship, but what is the relationship? Whether it is a positive relationship or a negative relationship, whether it is directly proportional or inversely proportional. Positive power increases with atmospheric pressure, so it is a positive. That is, it's a direct proportional. Okay, Padya, thank you so much. Okay, hope everyone is in the same page. This is how we any general thing what we will compare. Okay, so here there is a very weak relationship and there is a positive correlation. There is a positive, and this is something humanly we are seeing it. Okay, now what we have to make when we are creating a model, we have to make the machine to think the same way how we are seeing this particular graph and making decisions. Am I right? That is what machine learning is all about. Am I right? That is what machine learning is all about. So here we are having a weak relationship, but it is a positive relationship. Okay, so let me go to the code, and we have one more remaining thing, which is the relative humidity. Let me see how this relative humidity looks like. Okay, so I am having the relative humidity here now. Okay, why my graph is not coming? Yeah, it is coming here. Oh, great. Any impression on this? What is the relationship between my relative humidity and the power what I'm producing? First, whether it is weak or strong, good or bad? Strong, weak. So Ranga, how you are making this particular point? Weak. Is weak. Oh, it's not Mr. Ranga. I'm sorry. There is one more user. I don't know who is this anonymous user. Okay, but you are saying it is a strong relationship. No, it is not a strong relationship. You can see here it is highly scattered. It is not a clumsy one. Okay, a strong relationship or is something like this. Okay, something like this. I don't know why. What the relationship what we saw for the temperature and power output, you see here this is a strong relationship, because if we draw a line, this is my pen. Okay, if I draw a line here, okay, draw a line here, you see here I will be able to predict if someone is giving me this is my atmospheric temperature, and just imagine everything else is same. Okay, can you predict the power output? What I can do is say with an accuracy of say some 10. I don't know what is the unit of this power, maybe megawatt or I don't know. Okay, with an accuracy level of this much, I will be able to predict. Okay, so plus or minus 10, I will be able to predict it. But just imagine what we are getting here, okay, in terms of the last one, which is our relative humidity. Relative humidity, it is loosely packed. Okay, I cannot predict. I cannot predict anything with this. Okay, so that is why this there is a weak relationship. Okay, there is a weak relationship. Now, if you recall, in our last session, we build a model like this, something like this, with a number of breaks with respect to all other things. Okay. During that time, I mentioned about one thing. This is the individual contribution of each and every variable to break. Okay, that is how the model works. Okay, but there is something called interaction effect. When two variable changes, maybe one in plus and another in minus, there will be a different variation. Okay, so there is a combination effort. So too many cooks can sometimes spoil the food, and sometimes they can make good food. Okay, but whether they are spoiling or making it good, that also have to be seen. Okay, when one person is making the food, maybe something may be good. Okay, and the variance will be less. Okay, so like that, there is some interaction effect also we have to keep in mind. Okay, now whatever we have seen using the graph. Okay, now I have to make the computer to make the decision. Okay, how I can make the computer to make the decision? Okay, the variable what we showed in the Excel sheet. Okay, if I have to see how good is the relationship. This is something called the R square value, which we saw, right? Okay, in the same way, in this particular case, that is something called the Pearson coefficient, which will help us to make this particular decision. Okay, I'm going to show you what is this. Okay, so this is the correlation or the covariance between two variables. Okay, and this particular function gives me what is the covariance between what is the power I am getting and what is the ambient temperature or ambient pressure. Okay, and I can ask the R package to give me the covariance of all the variables in the data set, the power plant data set. Okay, so let me ask the R to give me the covariance. Okay, now it has given the covariance, and this is getting displayed in somewhere, stored in somewhere like this. Okay, so this is the variances. Okay, so what this variance all about? Okay? What is this particular number? And can we relate this particular number with whatever we have seen? Okay, let's have something like this. Okay, so what we are more concerned is about the PE. PE is the produced energy. Okay, PE and the ambient temperature, what we saw, it is having strong relationship or weak relationship. Do I have any chat? Okay, can I have some chat? Okay, so we were talking about yeah, good relationship here you have. Okay, great. Oh, great. I don't know who is that anonymous user. Kindly give yourself a name so that we can have some good interaction. Okay, no problem. Maybe in your next attempt you can do it. So we are having a strong relationship, but whether it is positive or negative. Bharat, yeah, great. Strong relationship, but whether it is positive or negative. Oh, Jeevan, great, great. Thank you. Okay, it's negative. Okay, so you can see here, what is the value here? Minus 0.94812. It is a negative relationship. PE with respect to ambient temperature, AT is ambient temperature. The number here is, it is showing a strong relationship. The value will be 0 to 1 actually. And here I am having something like 0.99 and it is negative. Okay, now let me go to the next variable. Okay, what is the variable here? It is the vacuum. Okay, so let's go to the next one. What we plotted is something vacuum. So we told like it is loosely packed, but again it is also having a strong relationship. But again here, like the temperature, it is also having a negative relationship. Okay, you can see here it is not so strong like ambient temperature. Ambient temperature is minus 0.94, whereas V is minus 0.86. Okay, so this is the indication what we are getting out of it. Okay, now let's go to the next one, which is the ambient pressure. Ambient pressure, we told like, oh God, what is this? It is more distributed, more loosely packed. Okay, it is having a positive correlation, but almost 50 percentage of the data is something not so. It's ad hoc. It's an more loosely packed. Okay, so you can see here it is having positive correlation. Okay, but plus 0.51 is the number or the Pearson coefficient what we are getting, which shows the relationship between the produced energy and the ambient pressure. Okay, now let's go to the next one. What is that? It is relative humidity. Relative humidity, again, it is loosely packed, but there is no trend line. There is no trend line. It is almost flat. Okay, so it is a very weak relationship. But if I make a trend line, it is a directly proportional trend line. So it is 0.389. Okay, and what about PE and PE? Obviously, both are same variable, so there will be very strong relationship. Okay, and it is 1. Okay, so this is what we can find out from the core functionality, COR function. Okay, core function. Now, as there are only 4 different variables in this particular case, we are able to do this, okay, very easily, not a problem. But if you are having multiple number of variables, okay, it will become very difficult for you. So we are having something called a plot called core plot, okay, which is normally used by many of the people for doing an exploratory data analysis, which will give you something like this. Okay, let me zoom in. Okay, and let me interpret the color. Interpret the color with the value what we are having. We can also have the value displayed in the color. It's not a problem, but here you can see. So what we have seen, the PE. Why? Okay, let me. Okay, so the power produced, okay, is in this particular row, and you can see ambient temperature is having a strong relationship, and it is having a color almost here. Okay, here. Okay, zero point 0.9 and some color. Okay, and you can see the vacuum is having a slight dull color. Okay, maybe somewhere here it is. Okay, and you can see the ambient pressure, it is having some blue color. Okay, maybe somewhere here. Okay, 0.51 or something what we see. Okay, and relative humidity is having a very weak relationship, but it is positive somewhere around 3. So the color is somewhere here. Okay, you can see here. Okay, so that is how we have to interpret this particular correlation plot. Okay, so now what next we have to do is, we can come to a conclusion like, was there is a relationship between the variables. So let we go ahead and create a model. Let we go ahead and create a model. I don't know what happened to my R session. Please give me some time. Console view. Let me close the session and open it. Okay, any doubts so far? It opens. There are some doubts. Let's give my computer some time. Any questions? Any questions? How was the audio and video? Was this platform okay? Okay, it's fine. Okay, Ranga, thank you. It's fine. Okay, then let me try to use the same platform. Sorry, friends, something happened to my R session. In between, there were some break, but mostly okay. Okay, audio break or video break? Audio. So what we heard is this particular platform allows up to 100 participants, but I don't think we will cross that particular limit. Okay, so it should be okay. We can continue with this. Sorry, friends, it is my R session is taking some time. Please allow it. Before that, I want to show you the paper what I downloaded for combined cycle power plant. To find it, but it was there. Quickly, I will execute the top rows over here. Okay. So we saw the color plot or the core plot. Okay, like this. Okay, I think I tried to move that particular image. Okay, though see our studio is free. Okay, sometimes free tools will be like this. Okay, now we know like there is a correlation between the variable which is produced energy and the ambient temperature, vacuum ambient pressure, and relative humidity. How strong, how weak that we will leave it for a moment, and let me create a small model out of it. Okay, so the model for that, what I have to do first is I have to create the data into two steps. Okay, the first step is I have to create a data set which is my training data set, and after that I have to do a testing data set. So actually, if you see this is a this if the data is simply given to us, this will become a time series data because it is a hourly average value of each and every variable is what they have given. Okay, unfortunately I'm not able to find the paper which describes this particular data set, but this is freely available. I can send you across for all the people who have registered with the email ID. Okay, or I will ask the organizers to send to you. Okay, but what happens is this is a time series data. This becomes a time series data if the data is raw given to us. What they have done is they have shuffled the data, like how the cards, the playing cards you shuffle. The same way they have shuffled with some random things, and they use some cross validation method to see that there is no trend or cycle or season what we have seen our second session or third session on time series forecasting. Okay, all these things they are eliminating and giving a data which is only having the values which is ambient temperature, vacuum, ambient pressure, and relative humidity, and what is the power they have generated. And they want us to use this particular data and create a baseline so that in future, if I know like tomorrow, this is the temperature of this particular hour, because the normal prediction from the weather stations will be hourly temperature and humidity and pressure predictions will be available from the weather station. With that particular prediction, will I be able to predict how much will be the maximum power what I can produce from the say the combined cycle power plant? If the power what they are producing is less than that particular baseline production, then they will think like there is some anomaly, there is some problem with the operations, and they will go inside and see like how the efficiency of the power plant can be improved. Then they will go for that particular analysis. Okay, this is the I would say like the shortcut or the latest way of how energy auditing is happening in many places. Okay, and I don't know how our people are using it, but this is a way people can use it. Okay, what I'm going to do is some random split. I have to do it. For that, I'm setting something called a speed called seed called 100. Okay, this is only a number which always gives me the same value. Okay, if I say I am not going to use this particular thing, then every time I create a model, it will give some value. Okay, so what I'm doing is I am going to create the split. Okay, it is the function called create data partition, which creates a split of the value. Okay, and this value I am giving the data set to power plant, and what is the y and what is the x, that also we have to say to the function. Okay, so I am saying like a y is power plant here. Okay, now I'm creating two data set, one for training, another for testing. Okay, now let me explore how this data set is. Okay, so you can see here the training data set is 80 percentage and the testing data set is 20. Okay, so if I have to change this, okay, then I have to just vary this particular value. Instead of 0.8, if I make it 0.75, then it is 75 percentage. Training and testing is 25 percentage. Okay, so this I am doing it, and now I am saying like using this particular data, which is the training row comma column. Okay, so row comma column 1 to 4. Use the first four columns, and you have your y, which is your fifth column. Okay, fifth column as your x and y. Okay, so the training function, if you just say okay, it asks what is the x, what is the y, and what is the method I'm going to use. Here, the method what I'm going to use is LM. It's a linear model. Okay, and I'm asking when you are making the prediction, please always scale it. What is scaling? I also told you what is scaling in our last class. Okay, there are min max scaling. There are a lot of methods which is used for scaling. Okay, why this scaling is required? Sometimes why this is required? Let me just spend some time here. So, what is the range of ambient temperature? What is the min and max or the range? Hope so. Okay, for plant, for plant, for ambient. Okay, so the range is 1.81 is the minimum and 37.11 is the ambient temperature range. Similarly, if I see the ambient pressure, okay, it is 992 is the minimum and 1033 is the maximum. So if you use the same data for making the prediction, then it will be more biased towards the ambient pressure. So what we will do is we will take the min and maximum, and we will create a value maybe between 0 to 1, a standardized value which is called scaling. And when they are doing the scaling, they also do something called the centering. Okay, they will center and scale. Okay, so that is what that particular code means. So please also do some uh, learning on basic statistics. Okay, I assume like as you are at least UG students, you have all this data. Okay, fine. So now I am asking it to train. You can see here the model is getting trained. Mine is a very small machine. It is only an 8 GB machine. So it has taken some time, and now I am training the data. Okay. Now let me see what is the result of the data. Okay. So what we saw there is the R square value, right? The same way here also we have something called R square value. Okay. The result R square value, we can take it out, and there is something called a root mean square value. Okay, this is another indicator which will show how good is my value. Okay, you see here my RMSE is 4.56. That means plus or minus 4. I don't know whether it is megawatt. Okay, if it is megawatt, I can be able to predict the power output plus or minus 4.56 megawatt. Okay, that is what the model can do. Okay, again, it is only the training. Okay, and the R square value is 0.93. That means it is a very good fit. The linear model, what it has created, is giving a very good. Okay, so now let me see what is the summary of the model, like how we have seen in our earlier cases of the loom, textile loom. Here you can see here the prediction, which is the power, how much that power plant will produce, is largely dependent on all these particular variables. You are having star, 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 three stars everywhere. Okay, and ambient temperature is having a very less p value. That means it is highly contributing, which we know based on the correlation what we have seen earlier. Okay, so the model is performing good. Now what I have to do is I have to test my model. I have teach the model how the pattern is, and now I have to test the model with the testing data set which I haven't shown to my student or my machine which I have trained in that particular data set. I am having something like a question paper with me, the testing data. Okay, with my testing data, I'm trying to predict. Predict is the function. What I'm going to predict, I'm going to predict using the value of a testing 1 to 4, that is the first four columns, and I'm going to use this particular model and do something called prediction. Okay, and I have the prediction now. Now, what I will do, I know what is the my predicted value for my testing data set. Now I have to calculate the square root error. Okay, square root error, so that I have the RMSE value with me. So the R square value is 1 minus the standard square error divided by SST, okay, which is the total sum of squares. Okay, so what is my R square? Let me see what is my R square value here. Again, it is a 0.93, which is almost equal to what I am getting. Okay, but here you see here I'm having something like 3, so round off. But if you make it 3, then it is 0.931. But my test value will be somewhere around. Sorry, my training R square will be somewhere around 0.937 or 8. Okay, so let's see how much it is. Okay, so what is the R square value I got? I got somewhere around 0.9281 in my training, but in my test, I'm getting a 0.931. It is better. It is good. It is performing well. Okay. Now we have seen by numbers whether it is performing well. But when you are giving a report to your client or someone, right, it is always good to put a picture. Okay. So what I'm going to do is what is the predicted value and what is the test real value. Both the things I'm going to club it into C bind is column binding. Okay, as a data frame, I'm going to do it. Okay, and now I'm going to use the ggplot function and give me a good plot of it. Okay, and this particular good plot now I can attach in my report. Okay, so what it says is what is the power my model have predicted and what was the observed power, the real power in my testing data set. You can see here it is closely packed and you can draw a line, and there is a limit which is what we have seen somewhere around 4.23 or something, right? So the gap between the outermost area of this, where is my Peter? Here, take a pencil, my pencil. Okay. So you see here, this is my thing, and the value between this and this is almost, say, this is 430, almost 5. Okay, almost 5. So it is 4.43 or 53 what we got as the number, right? So that is what we have. Line, draw a parallel line. Okay. Then I measure the distance between this line. It is almost 5. Okay, so that is my, what is that? RMSE value. Root mean square error value. Okay, that means it is plus or minus 5. This is only on the positive side, and we can also have a similar line on the negative side also. So negative side also, I can have the same line. This is my RMS. Okay. Any doubts on how we are interpreting with the model? Okay, output of the model. Any doubts? Now we have seen a linear model, okay, which also is giving a good result. But just to introduce you to some very good models, there is some model called extreme gradient boost model. Okay, we will go into this random forest and other things, but just to give you some feel of what it is and how this can be used. Having this package, that's why I install this particular package and show you what is an XGB extreme gradient boost. Till it get installed, if there are some doubts, please ask. Installed. Skip 1%. What I'm doing now here is again I'm creating the same partition. I'm having the training and the test data set. Okay, I'm using some libraries so that I'll be able to create this particular model. Okay, using the extreme gradient boost chain XGB. Okay, so here what I'm using is I'm using something called XGB, extreme gradient boost. Okay, using the training data set, and I'm saying like don't take the power as the input because I don't want to give the training uh, with power. Okay, so I'm saying like that is the Y for the model. Now I have trained it. I'm going to test it. I'm seeing the result of test, and I'm seeing what is the result I'm getting out of it. Okay, and I can also create some advanced things, and let me see what is my R square value or the root mean square value, okay, with an extreme gradient boost. So we have seen how a linear model works. Okay, now another piece of code which gives you how an extreme gradient boost works. Okay, and let me see what is the RMSE value it is giving. XGB is a little complex model, so it will take some more time for computing because it is one of the family of ensembles, a random forest and other things, which we will see in later classes, okay, how that works. Okay, very shortly, the result should appear here. Okay, if there are some questions, I'll be happy to take. Package is not installed. Yeah, you're right. I don't think tidyverse is required for this particular thing, but normally I will have all these things installed. When as my R session got closed, it got uninstalled. Any questions? With this, we will close the session. I want to just introduce you how complex models can also be built, so that in our next class we can work on some complex model. Any questions? Where do you stand on using Python instead of RStudio? See, it is not about Python or RStudio. We can work in both languages, but what is the intention that matters? Okay. Normally, we are having in the open market, it is like R or Python. That is how they will ask. But it is good to have both the language sample codes with us. So I will put it that way. See, if you want to learn a new language, you cannot go into deep, understand the syntax and other things. But normally, what I will do is I will work on that particular model. I will see some of the examples in the internet, try it out with myself, and save it like this, and then I will use it. So what happens is whether it is Python or R, I will have some sample codes for that. The same what I am doing here with XGB and linear model, the same I can do it with Python also. I have some data with me. Maybe during my next seminar or the next session, we will have the model built both in R and Python, and I will try to give you that particular kitty also. Again, it is not mine, right? I also learn it from internet. I also even learn from Udemy, the Triple IT Bangalore program, my master's program in LGMU. There are a lot of resources. From there, we take the program, we customize it, use it, and after that, keep it in our kit. It's nothing like someone's own coding. But obviously, when you are trying it out, for example, this is something what I'm trying it out from morning. Okay, so you see here, it is a very big data. Okay, having the data of somewhere around 79,000 patients. Okay, so then I am see sometimes you will not have some standalone functions immediately available for you. So I will try to create a function of my own. Okay, where and all I am not having. Okay, then I take the data, process the data. During processing the data, also I will find some struggle. Then I will make the function of my own. Like one of the function, what I want to make is like when the sepsis is detected by the doctor, some 6 hours before data, I have to work only on the data which is a 6 hour before taken in the ICU. I should not use the data which is within that particular 6 hours. Okay, so I want to filter that out. So how to filter that out? There will be some examples which will be there in our courses what we have attended in the past. But anyhow, any new data, it is something new. Then every time we have to customize the code such a way that matters to the intention. Okay, and sometimes I will also export the data into CSV outside because there will be some very easy things which you can do it with an R Excel kind of environment. So even I do that way, save it in CSV and again import it. See, Kali, friends, it is not about what program you are using, what tool you are using. Finally, the intention how to be met. Okay, for managing the intention, how easy tools you are using for achieving it, that matters. Okay, please don't break your head with R or Python or something like that. But if you are a starter, okay, please get familiarized with both the programs because sometimes the client prefers R, sometimes client doesn't care about anything, then we use Python because Python has good libraries and it is flexible to code. But R is not so, I would say, like, though it is a free open source, but less number of packages are there. And say TensorFlow kind of environment, Keras kind of environment, R has better connectivity to that particular places. Okay, so if you want a higher level things to be done, Python is always good. Okay, R is something like you start with that. Obviously, whenever you are doing something in R, there are cheat sheets. We call that a cheat sheet, like a bit for an exam. The same way there are cheat sheets which is available from an R code, how you can convert it into Python code. I think I have also one. I will try to share it with you maybe in the next session. So maybe in our next session, we will have a mix of both R and Python if you guys are interested. Okay. Any other question in this example data set available from UCI or other sources? This data set is from UCI. It is from UCI only. This CCP data set, this is from UCI. This is from UCI. But again, these data I have seen maybe in my studies. I don't remember. Probably, yeah, it is in UCA repository. You see here. Is there in UCA? Take it from UCA. There are some Kaggle competitions also on this topic have happened. See, there are some books also, beautiful books, and so on. It also is available. Please, yeah, this is the. It's from UCI. Yeah, this is the data set. This is the data set, and this is the link. See, yeah, this one. I have this paper also with me. So this paper will explain you how this data set is generated. Again, but very important is this data is yeah, say like yeah uh, yeah, real data actually. That is what the people claim that. Okay. So in our next class, we will see about some advanced topics other than linear regression and other things. Okay, we will go into regression analysis, but with some advanced tools. Okay, so that is what we will plan for the next class. If there are some doubts for this particular session, what we have seen, I'll be happy to answer. Otherwise, let's call it a day. Okay. By the way, from IAMP, there is a very strong communication. Like, please register in the link what the organizers are circulating. Okay, it will be there in the WhatsApp, or now also the organizers can post you that link. Okay, and the link of the recordings also. I request the organizer to just paste it in the chat window. Okay, please see the earlier recordings, though it may be boring, but just fast forward that particular video and pass it where and some good stuffs are there from me and or my fellow uh, presenters, and learn the things. And for whomever have registered, we will send you this particular code and other things also. So your email ID is very, very important. Please put your email ID. We can share this particular code, and you can also try it of your own. Okay, and in our next sessions, we will introduce you to some of the low code applications which are there for data science. Okay, like Climb or some very easy tools which you can straightforward use it. Okay, for the beginners, and for advanced users, we will also give you some cheat sheet of how from R you can go to Python and other things. Okay, that is what we have planned. Okay, let's hope we can do it. Okay, any questions? I want some interaction from the participants. Please unmute yourself. Give some remarks, positive or negative, please. Any remarks from the participant, please? You should unmute. You should unmute your mic and speak, please.
Participants, if you are not able to unmute yourself, please let me know.
Yes, sir. Yes, sir. You have to unmute your mic, sir. Yeah, yeah. Please click on unmute button. Yeah, it will be there in the platform. Yes, yes. Oh, okay, sir. Okay, okay. Yes, Mr. Upadhyaya. Yes, this can be applied to your existing plant also, provided you have a data. This is for existing plant only. This particular case study, na, this is for existing plant only. Let me show you the paper. I found that paper. See here, this is the paper. Okay, and this is basically the data set is for prediction of the full load. Audible. Okay. Hope you are all able to see my screen.
Yeah, yeah, I can see.
Okay,
Yeah.
great, sir, great. Okay, so you can see here, this is for the prediction of electrical power output of a base load operated combined cycle power plant using machine learning model. This paper is what describes about that particular data set. Okay, and this is the block diagram of what is that plant all about. Very important is many data set will be a synthetic data set, but this is a real data set. Okay, and you can see here.
The data it may be a difficult task. Get the data.
Getting the data.
Yeah. Getting these
Yeah.
various values for this humidity, pressure,
Yeah.
such a wide range of data. Getting the data in the existing plant may be difficult. No? What do you feel?
No, sir. Normally, you will be having some SCADA or DCS controlling this particular power plant. So from there, the historical data can be taken always, and from the particular data, the archive of that control system, you can export the data into an Excel, and then you use it for these kind. So this is a combined cycle. You can see here there is a gas turbine. Okay, and air inlet is very important, obviously, for the gas turbine. Okay, so the ambient temperature, ambient pressure, and relative humidity is the air which is going inside uh, to the gas turbine. After that, there is a compression, and then there is a turbine which is coupled to one generator. So the combustion happens here. The mechanical energy comes to the generator. Then gate for generating steam, and the steam turbine is there, and the condensed water is there. Again, it is a closed loop. So there is gas turbine 1, gas turbine 2. So this should be the block diagram as per this paper, which have contributed this particular data set. And this data set is given to the open world in 2014. 2014, and this is the paper describing it. Okay, probably for the participants who have registered, I request the IAMP team to send this particular paper also along with that. Okay, only within the closed loop group, because this is a paid version of paper.
Okay.
Okay, for academic purpose, obviously we can use it. So they have tried different, exactly. It's not confidential, sir. It is a public paper only. But this public paper, we have to pay and get it from, say, what is this? Yeah. So, so with for academicians, the taxes will be there. But for industry, it may not be there. But this is the analysis they have done, and you can see the same type of analysis only they have done. You can see they have done a linear regression, and they have seen try to predict it.
Yeah. Good.
And there is a reference also for this. So I would say it's a simple, but obviously it is not tried, as you said, in many plants. If we are able to do it, then it will be very nice. I can see some more chat. Very big. Please share your details and mail ID to this number. Oh, okay. This is the organizer, I think, IAMP team. Okay. So, Mr. Rupak Kandekar, you have asked, it may be possible to estimate the output of the power plant under various conditions of ambient temperature, atmospheric pressure, etc., and compare with the actual performance. Exactly, sir. Exactly. That is what, if you recall, in the in my earlier presentation, which I told, like, which was given to our the ISRE team. Again, as we are closely working, IAMP and ISRE. This is nothing but creating a digital twin. This is nothing but creating a digital twin. So what you have, Mr. Rupak, what you have told is nothing but how we are creating a digital twin. I will show you. Yeah, see here. So what we are doing is we are creating a model f of x. Okay, and say here we have created the digital twin of the fan. The same way you can create the digital twin of this particular power plant, and you can give the ambient readings here as the input and see what should be the expected power out. Okay, and compare with what the power actually it is producing, and if there is an difference which is drastic, maybe in this case the RMSE value is somewhere around 4. Say if it is more than 5, say megawatt or something, then that is drastically there is some problem. It is not the same captive power or the combined cycle power plant yesterday which have performed. Today there is some difference. It could be maybe some heat exchanger efficiency or some steam turbine efficiency. Some problem is there. Because of that, the problem is there. Okay, that is how they understand there is an issue. The large difference between the two may indicate some issue. You are perfectly right. Perfectly right, Mr. Gupta. So I also request please also go through this particular paper, which will give you a very basic idea of how a digital twin can be constructed. See, again, very complex things are also there, but this is something very easy to understand. Okay, sir. So any other questions?
Hope that paper will be shared to the participants.
Yeah, sure.
Okay. What you have shown, the paper, model paper, the paper you have shown, kindly request the organizers to share it to the participants, among the participants.
Sure. I don't know whether in the chat I will be able to attach. That is, yeah, I think I will not be able to attach. But probably if you have registered in this particular Google link.
Yeah. For the registered people, email will be available with the organizers. Yeah.
Exactly. Wonderful. Thank you, sir. Thank you. Any other doubts? If there is nothing, then we can close the session.
Thank you so much. Thank you very much.
Thank you so much.
Thank you, sir. Thank you for the wonderful session. Thank you, participants.
Thank you.
The next week details I will be sharing after something. Okay. Thank you all.
Good night. Thank you. Bye-bye.
Bye. Thank you.
See you.